All right, everyone. How are we doing today? Okay. You'll make it through the weekend all right? Wish that the weekend was longer. Yeah, definitely understand. We get, is it 2 weeks? We get 2 extra days? I forget. There's a fall break somewhere where we get Monday and Tuesday off. I don't remember if it's at the. Yeah, no, it's. We get a Monday and Tuesday in October, and then we get Wednesday, Thursday, Friday sometime in November for Thanksgiving. That's, I guess it's the week after midterm. That would be, I guess. Yeah, so 3 weeks. 3 weeks, not 2 weeks. Midterms in 2 weeks. Yeah, yeah. So the extra days actually are the 11th and 12th because that's Monday and Tuesday. The other days are the weekend days. Anywho, I have that earmarked for my side project catch up time. Okay, so let's pick up where we were um, on class before our break. It feels like a break not having class from Wednesday to Monday again. Kind of a long layoff, but um, we were talking about first order entropy. Forgot a hyphen there. Um, and what we want to do is write the associated MATLAB program to be able to do the computation that we discussed. And during the video for last lecture, if you want to go and review that, later on, in order to catch up on the theory, if you don't remember kind of the highlights of it that I'm going to hit here, then you can take care of that. But the major idea is that we are going to be computing this formula here. Okay. And this formula is composed of a few elements. The idea being that we have a message that is made up of m unique symbols. Okay. We, for the purposes of this exercise, are going to be using a picture and having the different colors that appear in that picture correspond to different symbols. So we're going to have numbers that are associated with each of the colors that appear in that image. So each pixel is going to be a symbol, and the color of each pixel is going to be what tells us the value of that symbol. We could just as easily do this with a text string, okay, where each character, letter or number, represents a symbol, and then we count the number of unique characters and use that as our value for m. Okay. Sorry, what? We're gonna put that back on screen again. That's half the reason I'm doing this. Is me taunting people with the clown picture. Anyway, Okay. P sub k is the probability that if we select a symbol at random, that we get the kth symbol in our list. Okay. So the way that we're going to compute pk is by taking the total number of occurrences of the kth symbol and then dividing it by the total number of symbols in the picture. So for us, this means, say we have color 17. We go through all the pictures and count how many times we have the color 17, and then we divide that by the total number of pixels. So that tells me the probability that a pixel selected at random will be the 17th color. Okay? All right, and is there anything else we need? Okay. And of course, H is our value for the first order entropy. So what we need to do is we need to go through and collect all of the relevant information for us for this problem so that we can put everything together to be able to compute this value here. Okay? This equation. We need to determine M, the number of unique symbols that appear in our image. Then we need to compute the probabilities. And then once we have the probabilities, we can compute the formula. So if we were making a simple flow chart, it would look something like this. Sorry. We input our message. We find M, which is the number of unique symbols. We go from 1 to M for each of our unique symbols. Okay. We take the number of the kth symbols that appear divided by the total number of pixels. And we loop through this. Okay, there should be a k plus 1 here too. Whatever. Okay. Do a loop, right? Loops and flowcharts are always dumb looking. Anyway, then once we have those probabilities, the last step before returning our output is we find the first order entropy because we now have computed all the necessary values. This will also be done in a loop, but I'm not writing another loop down. Okay. It'll be like loops that we've done last week for our computations for the perimeter stuff. We just have a value that we keep appending information to. And then we return H, 1, and then end. Okay, so this is the basic structure of the program. And what we want to do from here is to get into MATLAB. I'll give everyone just another minute to finish copying this down. And then jump into what we need to do here. All right, we got it. Okay. All right. So now we're ready to do some stuff in MATLAB. We give this a name. We can call it entropy. So we're computing the first order entropy of our system here. And what we want to do is set this up to where I'm going to change things slightly. I'm going to go ahead and make it to where the program also returns optionally the number of unique symbols in our message. Just fine. Okay, and what it is going to accept as its input is some vector v that's going to represent the message. Okay, so we'll call this message here. The message can either be an image, which is what we're going to be basing this on, or some kind of text message, and we'll show how those both should work. Okay. Okay, so this computes the first order entropy of a vector. And we're going to say that HM equals entropy message Okay, takes a numeric vector message and computes the first order entropy of that vector. Okay, we begin by computing or determining the number of unique symbols in that vector. we'll just call it the probability of each symbol so that we don't have to add in a whole other sentence explaining what it means by exactly what we mean by probability. Those darn hyphens, I keep forgetting them. Okay. So now we save this, and what we should see is if we highlight this over here, we get our tooltip down here on the bottom. And then also, if I type help, help entropy, we get our description. Okay, part of the reason why we do that. Okay, number one, so that we actually keep track of what in the world we're doing. Okay, and if we were being very, very diligent in typing up this opening block of comments, we would go through and very carefully define what all of the variables for the inputs and the outputs were and provide description of those. And then also, if it's a complicated function, give example inputs so that the user has some directive about how to use what these things are. Okay, we'll build up to that for that, but I just wanted to let you know that we're doing about half of what we should be doing. Okay, it's very lazy to do nothing here. That's bad. Okay, because you just have to remember what the code does or read it and then figure out how it's supposed to work, which is not nice. And then if we were being a little bit more careful, we'd spend some more time at minimum defining our variables here. But we've at least described in text what they're supposed to look like. Okay. So we're now ready to start coding things up. All right. Now, where we want to start is we're going to be using a built-in MATLAB command called unique. Okay. And this is going to solve one of the most irritating problems in this entire exercise, which is going through and determining the number of unique symbols that appear in our list. Okay. So it's going to happen sooner or later, so we might as well do it now. Our friend is back. Anyway. Oh, it didn't help. No, I actually think that's a very significant part of it. Is well, okay. So I think the reason why people who are younger than me find clowns scary is because it got popular in the 80s. And it, of course, being a Stephen King novel about a shape-shifting demon that eats children that takes the form of a clown. For those of you who don't know what I'm talking about. And there were a lot of people making children's cartoons who watched that and liked it. So they started putting increasingly creepy clowns in children's cartoons that lasted through the late 80s to the early 2000s. To the point to where companies that had very, very famous clown mascots like McDonald's, okay, stopped using that mascot because people have decided that they were done with clowns. But yeah, you've got your Krusty the Clown, who gets made fun of in The Simpsons all the time, who's not a good role model for the most part, and then the other like weird horror monster ones that show up in various birthday party episodes for children's cartoons and all that nonsense. Anyway, I missed all that, so I mostly think it's funny. No, I missed the trauma. Well, just, it didn't happen to me, I guess is what I mean. I evaded it. I evaded it, is what I meant. Okay, so the idea here is that what we're going to do is we are going to take our image, which the way that the image works in MATLAB is that it is a matrix that is a list of numbers. Okay? And that list of numbers corresponds to a color map. And the color map is a list where every row is an RGB value. Okay, so the red, green, and blue colors that are combined in order to create computer colors. And so what happens is that MATLAB looks at the matrix, and I have told it that I wanted to use the color map that is saved in this preloaded example. And so each of the pixels get the color of the corresponding row of the matrix. Okay, that's why the picture looked wrong and it was all blue before I told it to use the other color mapping. Because the default color mapping in MATLAB has more colors than the 81 it's going to turn out are part of this image. Okay, and so it was all in a very kind of narrow blue band for the most part. So we didn't get to see a lot of the variance in the picture, but of course using the correct color map color corrects everything and has all the pictures, all the pixels be their intended color. So that's what's going on there. Do you have a question? Okay. All I did was over here in the workspace, I just double clicked the name of the variable, and that brings it up. And then you can open any of the variables that you want, and I can actually edit the variables in here if I wanted to mess with something. I'm not going to do that. And it's very rarely the case that you would need to do that, but it is available to you if you're testing something or don't want to have to recompute a whole value. There's only one of them wrong. You can go in and fix it by hand. Okay. All right. So what this command here is going to do is it's going to take that matrix of values and turn it into a column. Okay, just because I want to pass a row vector or a column vector instead of a matrix. Okay, so that's going to be a bit of pre-processing that we do. We see here that I have 64,000 pixels in this image, which is kind of a large number considering how low resolution this picture is. That's how multiplication works. All right, we're going to have to deal with the fact that we're talking about pretty big numbers, right? This is not a computation we'd ever want to do by hand. Okay, so the unique command in MATLAB, which is the next step here and the first thing in our function, this is what is given to us here. What it does is it analyzes that big vector of 64,000 values and then returns to us that there are, in fact, as I said earlier, precisely 81 different colors that appear. Okay, for this example, it turns out to be the case that the numbers 1 through 81 are what this list is. Okay, it's exactly the list 1 through 81. For a general image, we can't assume that that's the case, right? That the list is going to be exactly 1, 2, 3, 4, all the way up to n. There might be gaps. So when we write our program, we're going to write our program in a way that can deal with the fact that the numbers may not be contiguous. We have U, which is our list of unique symbols. It is, I'll put it on screen here. It's the list of numbers up through 81. Okay, it has no gaps, but in general, we might have one that has gaps. So what we want to do next is make our loop, we will for simplicity's sake, we'll go ahead and define M. M is the total number of symbols or the total number of unique symbols that appear in our message. And so by measuring the length of U, which we know is a column vector, we can say these are the total number of unique symbols that show up in our image. And what we can do is we can make a list of probabilities using that value for M. Okay, so we're going to make P equal to a bunch of zeros, and then for these values, what we're going to do is we're going to populate this by going through and doing our list, right? Yeah. Mm-hmm. So one of the things that we haven't talked about explicitly so much, but is good practice for MATLAB and programming in general, is MATLAB allows us to do something called dynamic variable allocation, which means that I can resize variables on the fly as necessary, but that can slow programs down. So let me draw the picture here. And also make sure that that's still okay. All right. Okay, so let me demonstrate what's going on with dynamic variable allocation first, and then I will show you why we tend to avoid it. Okay, so let's say we have, oops, I meant to type X, but not to hold the button down. Okay, so we're going to make X equal to the empty vector. Okay, what I'm going to do is I'm going to make a loop that says for k equals 1 to 10. All right, and what I'm going to do at each stage of this loop is I'm going to say take X and append k to it. Okay, and we want to do it this way. And I'll go ahead and have that display on screen so I won't put the semicolon at the end. So what should happen is we'll take our old list and then add the current value for k to the list. So as we go through and do those computations, we see that each time the list gets longer. Okay? And it is actually the variable x itself that's being modified. Okay? So it's my vector is getting bigger. Now, if I do that, the picture that we want to see in our mind's eye here is when I start off, I have this little piece in memory that is reserved to hold the values that are stored in the variable x. Okay? Now, if I make x bigger, I need more space, right? But I I don't get extra space by just getting to automatically grab the space that is immediately next to x. Because after I have defined the original x, once I decide that I need more space, what could have happened is some other computer program has decided that it's going to use the space that is immediately next to the space that has already been used. Okay, so I can't use this because some other program has claimed it. So it is now necessary for me, when I need extra space, to grab it from somewhere else. Okay, I make x bigger again, but this space has been claimed by some other program. So I have to copy it over here, right? And what happens is we waste a bunch of time copying the same thing down over and over again because we're fighting with the way that the RAM for our computer is being allocated. All right, so we chew up resources here. What we do to avoid that is preconditioning our data. I know that eventually I'm going to need this much space for x. So I fill it up with zeros. And then when I make changes, I replace the values in the spot where they're stored. Okay. This is one of the soft like error messages, like pop-up things that'll come up in MATLAB, is if you write a bit of code and it says like this variable seems to be changing size at every iteration. That's what the warning is telling you to do, is rewrite it to not do this. Yeah. Yeah. You are reserving the space in memory that you know that you're going to need in order to do the computation. If we're doing short pieces of code that don't involve millions of data points or tens of thousands of data points or something like that, then we can usually get away with doing it this way. All right. But if we get into that, I have thousands of things going on, then that recopying process is extremely expensive. Now, it used to be the case that we always had to do some kind of pre-allocation operation for our older programming languages, because C and Python or C and Fortran and these other things were running on way more restricted hardware than what is available to us now. So you had to be very conscientious as a programmer about what resources you're using. And you had to do things like declare variable types before you were able to do stuff. Here, we just kind of type in numbers and it all works, right? But that's because MATLAB allows us to, MATLAB has something called mutable data types, which means it will change in the background the actual data type of the object that you're doing to be able to deal with the computations that are going on. For instance, if I take a real number and multiply it times a complex number, MATLAB just does it, right? But the real number and the complex number have different data types and behave differently. But MATLAB knows, well, real and complex arithmetic really aren't that different. I can just treat the real number like a complex number, multiply them together, and then report a complex number, right? In the olden days, you didn't used to get that for free. You used to have to be very careful about how you declared things in order for that kind of operation to happen. The other thing that would happen, and this is harder to demonstrate because of the way that we do things these days, but, whoops, sorry. Okay, is there used to be a more need to distinguish between an integer data type and a floating point value. because floating point values were more prone to specific types of computational errors than integer values. So if you're working with integers, you wanted to specifically do things with integers. Now, if I take a and divide it by 3, I get 1. I don't get 1.3 repeating, which is what I would get if I did this. Okay? So integer arithmetic puts me in the realm of modular arithmetic. It works differently. Okay? So because this isn't a hardline programming class, don't really get into the weeds with this stuff. Okay? And you kind of have to go out of your way to activate it in MATLAB. But a lot of the things that I will say and things that I will point out are related to these kind of underlying ideas that, if you didn't know to look out for them, can happen. Okay, so taking us back to this, we pre-allocate our data basically just to save the computer a little bit of time, and then also to make sure that we're a little bit more disciplined in how we write our code. All right, now we're ready to set things up. Okay. The first thing that we need to do is compute our probabilities after doing these initial setup allocations. We need to go through the list and find how many times each symbol appears in the value. Okay? So what I'm going to do is we're going to say for k equals 1 to m, we need to go through and count. So we need to go through every pixel in our image. Okay? So the way that we're going to do this is we're going to actually need to do 2 loops, right? Because we need to have a pass through that goes through and looks for every kth symbol, right? And then what we need to do is go through and do the computation for each, and we need to have another loop that goes through and looks at every pixel. So we pick a k, and then we go through every pixel. And then we pick the next k, and then we go through every pixel. Right? Pick the k, go through every pixel. Now, if we were being clever about this, maybe we go through and as we pick pixels, we delete all those pixels from the list and then use a refined list on the next pass if we were trying to make the program as efficient as possible. But that's trickier than what we're doing here. Okay? Maybe that's how we do it if we had a really high fidelity image and we needed to save time. Okay, the computer is going to do the program basically in a blink, so we don't have to worry about that. Okay, the way that we need to count this is going to be based on logical operations. Okay. So the way that we're going to do this is U is our list of unique symbols. Okay. We know that there are M total symbols in this list, and we are indexing with K. So if the kth thing in the U list is equal to a pixel, and we're counting through the pixels, okay, if those 2 values match, then what we're going to do is we're going to increase pk by 1. It starts off at 0, and then we add to it. Does that make sense? Okay, so this gives us a count. And we don't need anything else from our loop here. We just go through and do all that. Okay. And then, so that we do this last bit in one operation without spending a bunch of extra time, we divide all of P by message, so by the length of message. So what this does is it divides every one of our counts by the total number of pixels. We could have put that in the loop, but there's no reason to do it 80 times, and we can just do it once. This is just multiplying a vector by a scalar, right? Make sense? Yeah, so this loop, and the best way to deal with loops is to start all the way on the inside and then work your way out. Okay, if you're having trouble figuring out how to do things, mathematical functions work the same way, right? You start all the way on the inside with the very innermost function and then work your way out. So at this basis, we're counting whatever pk is, right? We know that pk is the probability. We're counting it. We're adding 1 each time under a certain condition. The condition that we add 1 is when the kth element of this list matches the nth element of the message. Okay? And we see here that the interior loop is looping through message. So we go through the entire image, and we're checking to see if the number in the image matches the current k that we're on. Okay? If it does, we add 1. If it doesn't, we don't do anything. We go through the whole, all 64,000 pixels, and add up all the occurrences of that number, which gives us a count. All right. I'm calling it P so that I don't have to relabel the variable name a bunch of times, but right now it's a count. And then after I have the count for all of the k different symbols, or all m different symbols, excuse me, then we divide by the length of the number of symbols in the image to get the probability. Okay. So we can, up until this point, we'll just put a breakpoint here, and then go through and run this to see if our probabilities are being computed correctly. Because if we are computing probabilities, what should we be able to ask ourselves about P to see whether or not what we've done makes sense? If I add up all the probabilities, I should get 1, right? Okay, so this is one of like the did we make a stupid mistake checks that we can do right now before we move on to anything else. Okay, so what we want to do is compute this value. We get down here to this. All right, we see that P has 81 values in it, which is what we expect, right? And what we want to do is take the sum of this. And we see that we get 1, which makes us happy because the sum of all of the probabilities is certainty, right? If I add up the probabilities of all possible outcomes, I should always get 1. Okay. We believe in this, right? The conservation of probability. Now, this is one of those conservation laws that doesn't get talked about as much as other things like conservation of energy or conservation of mass. It's just as important. Okay? If you're doing quantum mechanics, this is what you rely on, right? Is the conservation of probability. So keep that in mind. All right. So we can let this continue here. We get our valuations, everything's fine. So we divide by the total number of symbols to finish our probability computation. And now we are ready to progress to the next part of the program, which for us, fortunately, is pretty easy to do. Okay. We initialize h to 0. And in order to do the computation for the first order entropy, we just run another simple loop. We're going to go from k equals 1 to m. We're going to take h. And if you remember our formula for this, there was a minus sign involved here. Okay, so I'm going to do h minus the other stuff. That's not what I wanted. Okay. And so we take the probability for the kth element. We use the log base 2 function because the formula had a log base 2 in it. And go through and finish our computation here. Okay. So now we are ready to supposedly run our program to see whether or not it works. Yeah.
There's a green arrow that started when we started doing that. It's still linear on mine for some reason.
Green arrow. Yeah. Let me walk over there. Hold on. Tripping over stuff. There's plenty of room. Thank you. Oh, okay. So I'll explain that. I should have realized that's what you were mentioning. Okay, so let me put a breakpoint here. All right. Okay, so what I did was I added a breakpoint. Okay, the little red dot. That's what I did to stop the program and the other time so I could type in some stuff into the command window before the function finished executing so I could take advantage of the workspace for the interior of the function. As we see over here, It says workspace entropy, which means that we're in the workspace of the function and not the workspace of the console, which is what we had before, right? So we're in the little self-contained universe of the function. Okay. Right. Instance, if you've played enough video games to know what that term means. Anyway, now this arrow here is telling us where our current location is in the execution of the function. So if I press step here, what will happen is the green arrow will progress down to the next line in the code. Okay. If I press continue, what the green arrow will do is it will go down until it hits another breakpoint. Okay. If there are no other breakpoints, it will just finish the execution of the program, assuming that no errors occur. So if you have a reason to go through your function because you're trying to figure out what it's doing, or maybe when it doesn't work, okay, you can take advantage of these features to step through your program piece by piece in order to figure out what's going on. For instance, one of the things that you could do is use the step command here to go through and do one iteration of your loop at a time. If part of your loop works and the other part of it doesn't, and you don't know why it's doing that, so that you can carefully see how the computations are doing in your loop by maybe, say, typing in what does h look like or whatever to analyze your variables, or, as we talked about earlier, open them in the variable editor, because you can edit in real time your variables if you need to test things. I don't generally debug that way myself, just because you have to remember what you did, right? And then go back through and fix the code otherwise, but these options are available to you. Okay? So I'll remove the breakpoint. I will tell the program to continue. It will output its value. And actually what we'll do is we will run the program in earnest and get these two values, which I know from experience, having done the evil clown example a few times, these numbers are correct. Yes. Okay. Let me look. All right. So highlight that again. Sorry. Put your mouse over there where that left bracket is. You have a period instead of a comma after the H. Okay, open your function. You spelled length wrong. You spelled length wrong. All right. Something that takes practice is being able to like pull yourself away from what it is you're reading and be able to see where you've made mistakes. Okay. Now, me walking around and being able to see that stuff very easily happened for two reasons. Number one, I didn't write the code, so it's way easier for me to edit. Okay. Number two, um, I've done this enough times that I can step outside of myself and be very objective about what's appearing on screen. Okay. Now, that's harder for me to do for code that I've written because what you see sometimes is what you expect to be there, not what you typed. Okay. So, developing the ability to do that and to be properly self critical is a skill. All right. It's just like if you want to use kind of a sports analogy, when you're teaching yourself new body mechanics, okay? When you're trying to learn proper form with weightlifting, or if you're into yoga and trying to learn a new yoga pose or something like that, being able to adjust your perception of yourself and be able to make fine-tune adjustments from having a perspective other than just being someone else watching somebody. Like if you see someone else pick up a dumbbell wrong, it's really easy for you to tell them what they did wrong, okay? But it's a lot more difficult to be able to notice when you're doing it yourself incorrectly because there's certain angles that you can't see and sensations that your body has to train yourself to be able to experience, all that stuff. Programming is the same way, all right? It's also like writing an essay. You know, you have to pull yourself away from this is what I expect to see to what's actually there. Okay. All right. Now, one of the things that we can do with this now that we have it is use a different type of message, right? Okay. Now, this message is not anywhere near as interesting as the clown picture, as much as the clown picture is disdained by some of you all. Okay. What we can do is we can turn this into a list of numbers. Okay. And this is actually easy enough to do that we could do it by hand, right? Like it's a simple enough problem that if we wanted to verify this thing by hand, we could. But let's use our program and check what's going on with the entropy here. We have 1, 2, 3, 4, 5, 6, 7, 8. Wait, hold on. I miscounted. 1, 2, 3, 4, 5, 6, 7, 8, 9 unique symbols. Okay, so that part's right. I counted the 111 twice. That's why I was wrong the first time. Okay, so that part's good. And we see that this value here is a significantly smaller number than what we had for our clown thing, which I will remind you all was this. Okay, so we have significantly lower information entropy in the hello world message than we did in the picture. Okay, what that means is that there is a significantly less complicated message that can be encoded in the hello world thing than the clown picture. Okay, that's obviously for two reasons. Number one is because it's a way shorter total number of symbols, but also because there's fewer, we have repeated symbols in a shorter message, which lowers the sophistication of the message, right? E appears multiple times, or sorry, O appears multiple times and L appears multiple times. So it reduces the sophistication, right? And in general, vowels are one of the things that drop information entropy in text-based messages, right? A and E If you've ever actually had to go through and done some exercise in a lit class or maybe an English class, not literature, but go through and count occurrences of letters, it is stunning how many times E and A show up. Okay. And in a lot of passages of text, E is actually more common than A, which you probably wouldn't guess at the jump. You'd guess that A was more common, but E is at least as prevalent. Yeah, it's well, it's not the obvious answer, but if you think about it, you're like, yeah, that makes sense.
I mean, unfortunately, that's like without the gift. It's like, yeah, he's not going to be in your
Yeah.
right now.
Yeah. All right. Okay. So on a theoretical note for this, the value for the highest possible entropy that is achievable in this scenario is the log base 2 of m. Okay. What this value is the value when all of the symbols are equally probable. So if in our image here, all 81 colors were equally represented in terms of probability, then that's where we would have the highest possible first order entropy. Does that make sense? Okay. So that remember, we have to, we'll get rid of the picture. All right. If all of the symbols are equally likely, that's maximal entropy because that's maximal disorder, right? The likelihood of us selecting a individual pixel is the most random because it's equally likely that I would get any of the symbols in that image. Okay, so that's maximal entropy. The average state is the most chaotic, would be another way to think about it. And if there are certain symbols that are more prevalent than other symbols, that drops the entropy because I'm more likely to get one of those other symbols. So for instance, one of the things that we could do is we could isolate regions of the picture that happen to have like all one color. Like if we looked at the clown's nose, okay, we would expect the information entropy in that part of the picture to be a lot lower than in other parts of the picture or the picture overall. Okay? That's why if you need to go hiding messages and stuff, you hide messages in the busy parts of the picture. Okay? And assume that obviously the person looking has to know where to look. But that is the better plan. Okay. So we let that one breathe. All right, but I do hope it was helpful in terms of programming exercise and really thinking through how to put all this together. Now, what's interesting about this is there are some things that we can do that would make this program a little bit shorter. Okay, so let's move this over here. Okay, and what we'll do is we'll just copy and paste this. Oh no, I can't do that. I'm scared. Okay, delete. So I don't make that mistake again. All right, we did it. It's very, very, very vexing. That the copy and paste stuff is so silly. All right, so um, we'll I will start with the less mystical tricks and then move into the more mystical tricks. So we'll start at the bottom of the program and then work our way up. All right. Now, one of the things that we can take advantage of in MATLAB is really nice is MATLAB is very, very good at doing matrix-based computations, right? So if we have this kind of computation where I'm computing a sum, okay, one of the things that we can do is for this sum is MATLAB has a command, and I used it previously, called sum, right? That just takes a vector and then adds up all the stuff in that vector. Okay, so it stands to reason that there might be some way for me to use that command in order to replace going through a loop to do all that, right? If I could compute the vector that held all of these things, right? I could compute all those values. I could take each pk and then I could multiply by the log base 2 of the probabilities and then multiply element wise and then everything up, right? Seems fine. Okay, okay. All right. So this is a problem with the virtual machine, like the HiPEC thing that I showed everyone how to, or everyone to log into. Okay, so the way that this works is that the thing that gets added to your clipboard is the most recent thing that you select. So this is now in the clipboard because I selected all this stuff. So what I had to do was delete the other thing first, all like the boilerplate text, so it was just blank, and then copy and paste. Because if you select the other part of the text second, it overwrites whatever's in the clipboard. So very annoying. All right. So what we can do, did you get it? All right. So what we can do is we can say that, actually, I want to do this up here. We can do it. We can do it in one line. The sum of p element-wise multiplied by the log base 2 of p. Oh, we need a minus sign. Okay, this works because we take all the probabilities and then multiply them element-wise by the logarithm base 2 function, which works element-wise on all of the p-values. And what should happen is, and what I will do is I will call this h2, okay? This h minus h2 should be the 0 vector. And what I'll do is I'll just put this in norm so that instead of getting 80 different numbers, or sorry, we'll only get one number anyway. If I were comparing probabilities, I'd have to do the norm, but this, since it's already a scalar, I don't have to worry about that. Okay, so now we check this. Oh, whoops, sorry, I forgot to put a 2 here. This is the part that compares the new entropy calculation to the old entropy calculation. It's a 0, which means the two numbers that I got were the same. Okay. That means that this can be replaced with that one line. Okay. And in fact, That's not the only way we could have done it. We can also type this, which is the transpose of the column vector p times log base 2 of p with a minus sign in front of it. Okay. What that looks like in practice is I have a column vector, which is p, or sorry, a row vector, which is p times a column vector, which is the log base 2 of p. And by matrix multiplication, it's a dot product, right? The sum of the component-wise product. Okay, so either one of those would work. Then I will leave this one, the one that's uncommented, and test it real fast to show you that we do indeed get the same answer. Huh? Well, I mean, any particular program can be written in a myriad of ways, right? But there's for that bottom piece, there was a loop, which is like the way that I would expect you to know how to do it or be able to figure out how to do it. And then there's more clever ways involving what we refer to as vectorized computations that do the work of a loop but look more like a mathematical formula. Okay, so like this bit here, you have to know that this is a dot product, which is why this works, right? There's a lot leaning on the fact that this is matrix multiplication. The fact that that's a matrix multiplication is what makes that all work, right? And there's kind of a cleverly hidden transpose here, okay? So what you would probably do, just to make it easier on someone who's reading this, is let them know, like clue them in that this is a dot product, okay? Or there's an actual dot product operator in MATLAB that you could use, a dot product function, okay? We've only got a minute left, and there's more fanciness required in order to make this simpler, but it's actually possible if you use a built-in MATLAB function to not have any loops for that part too. Okay, getting rid of one of the loops is pretty simple. Getting rid of both of the loops requires you'd have to look up some function in MATLAB that is designed to do this kind of thing, sort of deal. Okay, so what I'm going to assign for all of you as an informal assignment, okay, something to work on between now and Wednesday, just as practice, is to look at this and see if you can eliminate one, if not both, of the loops that appear in this block of code. Okay? And what I'll do, and send me an email, someone, tomorrow morning if I don't remember to do this after I ate dinner tonight. But I will post what we have so far on Blackboard so that you have a working copy to begin with. Okay? And then you can play around with trying to get rid of the one or both of the loops in that first probability computing structure. All right? Okay. I will tell you that the trick involves comparison operations, right? You're doing something like this. Okay? You need to make sure that you're counting, and there are ways to do counting and add, and there are ways to do counting and ways to do addition that will make things easier. Okay? And there are other types of indexing commands that may be useful, like the find command would be something that would be one of the paths that you can use in order to simplify this. All right? So take care, everybody. I will see you next time.